she has one patent in applied status and one patent being granted. Her core areas of research interests are microwave for solid waste management, advanced oxidation process for waste and wastewater treatment, development of novel catalyst and its characterization of catalyst for biorefractory pollutant removal, and agricultural and industrial wastewater treatment. I welcome you, ma'am, to the session. Thank you.
Thank you so much for the nice introduction, and thank you the organizers for having me here to have the opportunity to share my research with all of you, all the participants here. So before going to the session, let me just share my slides.
Yeah, it is visible. It is visible.
Okay.
Only thing, it need to be in the presentation mode. That's all. Okay. Yeah. Yes. Yes. Yes.
It is in
Yes.
presentation mode, right?
Yeah, it is in presentation mode now. Yes.
Okay. Okay.
Okay. Okay.
So, warm good morning, good afternoon to all of you, and hope all of you are safe in the current pandemic situation. So I'll be just talking about some research that we are doing in the pyrolysis on a sustainable waste management. So as we all know, we have a solid waste generated from different sources. So maybe like the household waste, generally which is classified as the municipal solid waste. And we have the hazardous component mostly generated from the industry. So am I audible to all of you?
Yes, ma'am.
Yeah. Yeah. Yes.
Okay. Okay. Thank you. Yeah. So the industrial waste, most of them will be categorized under the hazardous waste category because of its toxicity, reactivity, and so on. And we have the other category which contribute to the solid waste in a large amount, that is biomedical waste or hospital waste. And I know this has a lot of relevance in the current situation because we have huge amount of the producible or biomedical waste that is generated due to the PPE kits or the other essential things that is used for COVID patient treatment. Yes. Now, what should we do with this solid waste generated from different categories? So the purpose of effective management is to control from the generation point of view, then as and when it is generated, the proper storage, collection, then transfer and transport to the processing facility, and as far as possible, reuse, recycle, and then dispose the solid waste which is of no use, right? But in doing so, while carrying out each of these steps, we have to go with the principle of more closer to the public health aspect, the economic aspects, with suitable engineering techniques so that the prevention of waste to the pollution to the environment will be minimum. And same time, the environmental conservation, aesthetics should not be deployed, and also other environmental considerations. I'm sure you all are familiar with all of this, the solid waste generation and management techniques as well. But in today's talk, I'll be mostly concentrating regarding the municipal solid waste management. So as we all know, what all composed of this municipal solid waste? Of course, the waste generated from the individual household. And we have a huge contribution of MSW that is being generated from the agriculture. And India being an agricultural country, we have a lot of agricultural residues being produced, which will account to the total MSW. And of course, the waste coming from the commercial and business establishments. The non-hazardous component of waste that is coming from the industrial area, and of course, institutional waste, and the sewage sludge generated from the wastewater treatment plant. All of this will add to the MSW, which is to be handled properly. Now, why we are more bothered about the MSW treatment or disposal? If you just take the Indian scenario, as we know, there is a huge increase in the MSW generated day by day. As per report, if you see in the last 30 years, our MSW generation has almost doubled. So we can see now the waste hill that is there on the outskirts of the city, where the city is dumping their solid waste. And if you take the global scenario, of course, we are on the higher side or the ranking first in the case of the solid waste generation. And the total estimate you can see on the right side, like in 2016, estimate is around 277 million tons of waste that is being generated by our country annually. And of course, the projected waste generation is almost double by 2050. And same is the scenario with the country which is just behind us in solid waste generation, for example, US, China, Brazil, and Indonesia. You can see there is a drastic increase in it is almost projected, but even then it is the trend, that is the drastic increase is there in the MSW generation with years. Now, what causes this increase in the MSW generation? Of course, one credit goes to the population increase. More the population, more will be the waste generated because of the per capita generation. And then is the increase in standard of living, right? Standard of living will procure more than what we can consume, and most of this is going to the waste. So the waste generation is increasing with respect to the standard of living as well. So this exponential increase sometimes make a question whether we can manage this increased waste with the traditional method. So if you see the traditional method that is practiced age long, the simpler method that is open dumping. Or maybe if you take the case of the city, they will dispose this waste in the outskirts of the city. Now the thing is, the city is growing and the waste generation is increased. So we can see now the city border is merged with the dumping site. And most of the time in the urban area, they are running out of place for waste treatment and management. Now, in recent, all the budget, you can see there is a tremendous emphasis on innovative and environmental friendly initiative for this waste management. It is not only waste reduction or waste treatment, but to derive the fuel, so refuse derived fuels, to get the refuse to be used in the form of fuels, or to convert this waste into usable energy. So today, in today's talk, we will more focus on the waste to energy techniques of MSW. So before going to that, what is the current scenario? Although we have a lot of engineering techniques and methods available for solid waste management, the most practiced method of solid waste management in India till date is open dumping. So we are just dumping our waste, and as far from our backyard, we are happy. So the NIMBY concept, not in my backyard. So it is far from my home or far from my surrounding, I'm happy. But when you do this open dumping without pre-treatment, sometimes there is no liner beneath the dumping site, or it is not covered properly. So in both these ways, it may cause either the groundwater pollution or air pollution. Yes. Now, if you see the total amount of MSW, again, this is 70 to 90% of MSW disposed. So if you see the 70 to 90%, it is only a very less fraction of MSW that is being collected. Now, from this collected MSW, around 70 to 90% is dispersed in unsecured landfill. Again, I'm sure that you know what is a secured landfill. The landfill which has a proper liner at the bottom so that there is no leachate penetration beyond this landfill liner into the underneath soil. And it will also have a proper landfill cover, right? So if you don't have a secured landfill, this uncontrolled dumping sites, although it is inexpensive and convenient, it will cause the groundwater pollution because of the leachate that is penetrating into the soil, or it can cause the air pollution because of the emission of methane, carbon dioxide, carbon monoxide, and other toxins. So both way, it is an environmental hazard. Now, if you again take the landfilling that is mostly practiced other than open dumping in our country, how far we can sustain without landfill with the increased generation of waste. So we have plenty of landfill in our country. For example, we have the oldest landfill in Ghazipur, Delhi, and one of the Asia's largest dumping ground, that is in Mumbai. If you see the scenario, by a decade ago, around 2002 or so, all this dumping site is exhausted. So its capacity is exhausted, but even today, the dumping is continued in this landfill, mainly due to the lack of an alternative land. But then we have the incidents of some hazard, some safety issues from these landfills. For example, in Delhi garbage dump, there was it caught fire due to this refuse that is being dried and then caught fire, and it took around 3 days to douse that fire. And if you see that Ghazipur dumpyard, there was an incident of that landfill collapse due to heavy rain, which caused the death of 2 persons and so on. So that means most of that landfill in our country is again running out of its capacity, beyond its capacity. Right. So we have solid waste management rule from 2000, and it was amended in 2016 also. Again, I won't be going deep into this. Probably you might have heard this in the previous lectures, or you know by yourself earlier as well. So let me just highlight the MSW management tool that is relevant as for this particular topic. So we have now the recent solid waste management rule handbook, that is the latest is in 2016 with recent amendments. And there are separate rules for plastic management, e-waste management, biomedical or hazardous waste management, etc. But if I take again in particular about the solid waste management rule, the generators are the prime important, because the source segregation. Who should do the source segregation? The person who is generating it. Yes, it is the generator's responsibility to perform the source segregation. And this source segregation is very vital, because each component of your solid waste may need different type of treatment. And many a time, the segregation of solid waste is the bottleneck for most of the solid waste management techniques. Right? So to have this source segregation and proper collection, they have, even the amendment says, a pay user fee. So we are paying a user fee for the waste collector.
Request the participants to mute their mic, please. I can do from my end, but I want you to do it from your end itself.
Okay, let me continue. So the user fee and sport fine for littering in the unrestricted space, right? And the other thing is, if as far as possible, the biodegradable waste we can manage in a decentralized system, for example, the composting system or anaerobic digester at domestic or community level, etc. And for those waste component which is non-biodegradable, they can even have a collect back system. For example, the packaging material. To implement it further, sometimes it is practiced, especially in Western countries, like we may need to pay little extra. For example, if you are buying a PET jar, we may need to pay little extra while buying it, and the extra money will be returned back once you return the empty PET jar to the customer. So that way, collect back system can be implemented. So this will enhance the recycling process. But above all this, now the concept of RDF and waste to energy is gaining more and more emphasis or importance, because even if you have lot of source segregation, techniques are there, but there is not much in practice. So what we need to do is, the waste is obviously generated, so we have to make use of most out of it instead of just dumping the waste into the backyard. And the waste management strategy, which is again familiar to all of you. So we have to go towards the sustainable consumption so that the waste production is very minimal. So as far as possible, the source reduction, right? If not, the next viable option is to reuse or recycle. And if none of this is viable, then we are going for treatment, and the least preferred option, of course, is the disposal. And we are doing it in a sustainable way that is environmental friendly, economic, and socially acceptable way, so that we can have a sustainable waste management technique. Now, again, coming to the waste to energy technique. So there are different types of waste to energy technique, and most all this waste management, waste to energy technique is emphasizing the SWM handling rule of 2016 and trying to generate maximum out of the waste with minimum pollution to the environment, right? Okay, you can have different routes of these waste to energy techniques, say thermal process or biochemical process, mostly the biochemical process where we are using the microbes for the degradation of waste. So this will be only option for the biodegradable component. Now coming to thermochemical, broadly we have the incineration process, gasification or pyrolysis. So I'll be focusing more on the pyrolysis technique, one of the thermal degradation process. And in pyrolysis, mainly we can achieve the volume reduction of around 88%. So thanks to this high volume reduction, which will consume very less amount of land as in case of direct dumping into landfill. But it is not only the volume reduction that is achieved by pyrolysis. We can also get value added byproduct. So there is a solid component that is biochar, liquid component bio oil, and the gaseous component usually known as pie gas or non-condensable gas. So in addition to this value added product, we can also recover the heat generated from this thermochemical process through heat exchangers in a suitable way. So in brief, what is a pyrolysis technique? So in pyrolysis, we are heating the feed in a pyrolysis chamber. So here is the pyrolysis chamber, and the main difference between incineration and pyrolysis is in pyrolysis, the reaction is taking place in absence of air. Of course, we are going for high temperature, but again, the temperature may not be as high as an incineration process. Maximum 500 to 800 degrees Celsius is enough for the pyrolytic reaction, and this is carried out in the absence of air. Now, once this pyrolysis is done, usually we may get the solid product, that is char and the vapors. So to make sure the reaction is taking place in the absence of air, or I should say in the absence of oxygen, usually the pumping of the nitrogen, helium or vacuum is done so that the oxygen atmosphere is prevented, right? Now, after this pyrolysis reaction, of course, we have the solid product, biochar or char, and the rest is the vapor, and this vapor can be condensed. So before condensation, if required, so it's again up to you in the pyrolytic design, you can go for a catalytic conversion to tune the byproduct that is formed during the pyrolysis process. Now, after this catalytic conversion or directly, this vapor can be condensed. Now, the condensable fraction will be converted to liquid. This is our bio oil, and the rest will be the pyrolysis gas. And most, unlike the incineration process or the simple combustion process, mostly the pyrolysis gas will constitute hydrogen. Of course, there will be some methane and carbon dioxide, but most of the time it is hydrogen, and further you can improve the hydrogen production during pyrolysis by this catalytic conversion. Right? So we got the three products, the char, the liquid, and the gaseous product, and the heat recovery can be mainly done in the condensation stage or further from the gaseous stage through heat exchangers. Now this reaction can take place based on different reactor systems, maybe fixed bed, moving bed, fluidized or rotary kiln. Rotary kiln is the mostly practiced pyrolysis reactor, even though fluidized bed can give more efficiency. Fluidized or moving bed may give you more pyrolytic efficiency compared to fixed bed. Now, is the waste suitable for pyrolysis? What should be required for pyrolysis? So we have to heat up our waste component. It has to go to a temperature of 500 to 800 degrees Celsius or so. So what should be the requirement or quality of the feed to be pyrolyzed. Of course, it needs to have a high calorific value, and most of its components should be volatile so that it can be pyrolyzed and volatilized into byproducts. As heating is required, lesser moisture, the better will be the pyrolysis. Otherwise, the latent heat of vaporization will consume some of the heat energy, beyond which only the pyrolysis reaction takes place. And to avoid the air pollution, the less should be the nitrogen content or sulfur content in your feed, so that SOx NOx emission can be reduced, and low ash content. So if you have more inert material, again the pyrolytic efficiency is less. So just to remove this ash content or the inert material, the minimal separation can be done, that is the separation of glass, metals and inert material prior to the pyrolysis process. So again, so let me just take it. So does all our waste component has this quality that is required for pyrolysis? So let me just take few components. We have food waste, paper, cardboard, plastic, textile, etc. will be there in our municipal solid waste. Right? And if I take the inert percentage, so inert percentage in food waste is very less. So can I take it for pyrolysis process? No, because if I see the energy content or calorific value, it is pretty less. Paper, again, the inert content is less. I have a high calorific value here. So it's better for thermal conversion. So is the case of cardboard. Now, if you see plastic and rubber in the list, the plastic and rubber comparatively less inert material and very high energy content. So very good for the pyrolysis process. So based on this principle, we have plenty of pyrolysis plant running in our country, especially for the plastic and rubber conversion. Let me quickly go through the different pyrolysis plant that is commercially running in our country. So here we have Uflex plant that is in Noida, which has a daily intake of around 6 tons. It takes LDP, high density polyethylene, polypropylene, etc. Mainly collected from the North India. Only the shredding and initial inert material segregation is done. And after the pyrolysis process, 300 liter of fuel is produced on a daily basis. Of course, this has the 3 fractions, that is light distillate oil, hydrocarbon, and carbon black, or this is the biochar. Right? The 3 components are there. We have many more. For example, the Tirumurti productions in Madhya Pradesh has even higher capacity, that is 15 tons. Again, they are producing bio oil, hydrocarbon, and carbon black as the 3 byproducts from the plastic pyrolysis. Yes, the one in Chennai. Again, this is now running on a trial basis. This is again a plastic pyrolysis plant in Chengalpattu, mainly to process the plastic waste, and bio oil or pyrolysis oil is the major component of the byproduct or end product that they are aiming at. Right? So this is again an alternative for the plastic waste management or recycling. We have many more, KGN in Telangana, but here they are doing for waste tires. Of course, we have seen rubber and plastic. Rubber, plastics, they have high calorific value. So of course, well and good. This is a good feed for the pyrolysis plant. So waste tires can also be pyrolyzed to get the 3 byproducts, again bio oil, biogas, or pile gas or biochar. Yes, this plant is also in place. And this is the AP Chem in Mumbai with 12 ton of daily intake, who is pyrolyzing the multi-layer packaging waste. Again, this is a plastic waste. So size reduction is done. And the gas, bio oil, and carbon black is taken as the output. So you have, I have even given the link of each of this plant, which is up and running in the country in the slide itself. Maybe you can have more details about the plant while going through that link. But being said that, we have different pyrolysis plants set up in our country for the pyrolysis of the tires or plastics. Yes, one more here we have in Madhya Pradesh for waste tires, rubber, and plastic. So if I just summarize some of the plants that is up and running in our country, we have the pyrolysis plant for the plastics, we have pyrolysis plant for waste tires, right? But does it give a complete solution for our MSW? So how much component of our MSW is plastic or tire? We can see a very less fraction, right? A very less fraction. Here we have the plastic and rubber. So on a rough estimate, it is around 4 to 6% is the plastic or rubber component in our municipal solid waste. Then this can be easily pyrolyzed, but that is not giving me a sustainable solution for our MSW management through pyrolysis. Why? Because we have a huge composition that is food waste. We have another component that is paper, which is produced in large quantity in our MSW, but cannot be pyrolyzed due to in the conventional pyrolysis unit. Again, if you see the component of food waste, how much is generated, right? If you see around 1/3 of food produced in human consumption ends up as food waste. So it's the same concept. We'll afford, if you have money, we'll afford more than what we can consume, and the rest will go out waste. Right. So in that way, we have a huge annual generation of food waste. If you just take in different countries the food waste generation, how it is in Hong Kong, around 8-10 tons per day, Australia 2,100. So the difference is mainly in the living standard, and we are at the top thanks to our huge population. So that way we know there is lot of food waste that is being generated on a daily basis, and this is constituting a major component in the municipal solid waste, but which is not yet pyrolyzed using any conventional technique. So why conventional pyrolysis technique fails for food waste pyrolysis? The answer is here. If you see the moisture content, so I'm pretty sure you know the proximate analysis of solid waste. So let me just quickly go through what is a proximate analysis is. Basically, we can see the chemical composition through proximate analysis. Maybe the standard method AFA can be used to determine these individual components. For example, moisture content can be determined by moisture loss after heating in an oven at 105 degrees Celsius for 1 hour or so, continue till you get a concordant weight. And if you increase this temperature to an ignition value of 950 degrees Celsius, the difference in weight will give you the volatile matter content. What is left behind is the fixed carbon and the weight of residue after combustion. That is your ash content, right? So we can categorize, or component wise, we can see what is the moisture content, volatile matter content, fixed carbon, and ash content in your waste. So if a waste to be pyrolyzed, we have to have a very less moisture content and as far as possible high volatile matter content. So here comes the quality of our waste. You see the proximate analysis of food waste and garden trimming, it is more than 60%. So obviously it is very difficult to take it for pyrolysis because all the initial heating up procedure will consume the energy for the latent heat of vaporization, that is to remove the moisture from your sample. Else you may need to go for a preheating technique. And even after doing so, we will not get much energy gain. Okay? So that is why food-based pyrolysis is not yet in practice. Now, if you see further about the property of this different components in solid waste through ultimate analysis. So ultimate analysis will give you that elemental composition, that is percentage carbon, hydrogen, nitrogen, and sulfur in your solid waste sample. So maybe you can use the CHNS analyzer for quantifying this ultimate analysis. Then, where is our individual component with respect to ultimate characteristics? So in ultimate characteristics, if you see the paper, food waste, wood, green waste, all these have a percentage carbon of around 43%. And on the right, you can see the percentage oxygen. The oxygen in percentage oxygen in food waste is much high because we have mostly carbohydrates present in food waste or even in green waste. That adds up to the increase in the oxygen content. Right? But then where is the position of our plastic waste with respect to the ultimate characteristics? So if I see the composition of plastic waste, it has around 84% carbon. Well and good. And at the same time, it has high percentage of hydrogen and comparatively less, or I should say very less percentage of oxygen compared to other solid fractions. So let us just keep it in mind and move forward. That is high carbon content, high hydrogen content, and less oxygen content in plastic waste makes it a good pyrolysis option, pyrolysable waste. Why is it so? Because if you see the calorific value of or the heat content of any waste, that depends on the carbon content and hydrogen content. Maybe you can directly calculate the calorific value of a waste using digital bond calorimeter, or even you can use Dulong's or modified Dulong's formula to roughly calculate what is the calorific value of your waste. So if I take the calorific value with respect to the carbon and hydrogen and oxygen, as we have seen in the previous slide. So here we can see if we have high carbon content, high hydrogen content, obviously adding to the high calorific value. So high calorific value and low calorific value. Again, this is the heat liberated from your sample once it is brought back to say 150 degrees Celsius or so. That is the high calorific value. Sorry, low calorific value. And the heat liberated once it is brought back to the room temperature. That is the high calorific value. Yes. So you can see this high calorific, the calorific value in turn depends on the carbon and hydrogen in a positive manner. So it is improving the calorific value, whereas the oxygen will reduce the calorific value. So we know our food waste with much high oxygen content has a very low calorific value. So should I again take this waste in the pyrolysis process? Because it has a very low calorific value. It has high moisture content. But then let me just go through the thermogravimetric analysis. So in thermogravimetric analysis, we can just characterize the waste in terms of its weight reduction with respect to temperature, right? So how resistant is our food waste or plastic with respect to temperature? So if I take you here, in the top, we have the thermogravimetric analysis of food waste. So here you can see the food waste weight reduction. So initially it is if I say 100% weight. So when the temperature is around 100 degrees Celsius or so, so here we have a less reduction. And further within 300 degrees Celsius. So at 300 degrees Celsius, we have a huge reduction in the weight of the food waste. So here initially there is not much reduction because it was a pre-dried food waste. Otherwise, there will be around 70% reduction due to the moisture content removal. But this is a typical sample which was pre-dried. So around 7% is the moisture removal here. And rest you can see within 300 degrees, there is a huge weight reduction, which is further confirmed with the DTG curve, the differential thermogravimetric curve. So here you can see the rate of change of weight with respect to temperature, right? So DTG curve again says that means around 300 degrees Celsius, the food waste has a higher volatilization potential. Now we have several pyrolysis plant up and running. What is the temperature requirement in this pyrolysis plant for pyrolyzing your waste? So here you can see the temperature of a LDPE, for example. This is low density polyethylene. To reduce its weight significantly or to cause a significant weight reduction and volatilization, we have to go to a temperature of around 500 degrees Celsius. So what does that mean? For a plastic pyrolysis, I'm improving the temperature to 500 degrees Celsius, and my food-based pyrolysis can happen in comparatively lesser temperature. But why again we are reluctant for food-based pyrolysis? Because food-based has high moisture content and very less calorific value. So do we have any way out? Because when you think of the conventional pyrolysis, by seeing all these property of waste, what we can tackle with is only the plastic waste and waste tires. There are many other components in our solid waste like biomass, that is the plant or animal residues, or even some other agricultural products, livestock waste, forestry, fishery, the non-hazardous industrial waste. So all these are there constituting a major component of your solid waste. And then addressing the plastic and waste tire by pyrolysis is not a sustainable waste management technique using the pyrolysis process. But then the property of all this waste makes us reluctant to go for pyrolysis because of its high moisture content, less calorific value, and so on and so forth. So if you just see the typical MSW composition in different cities, this is not only food-based. So here we have the MSW composition. So it has the plastic, garden trimmings, all those combined together. But this gives me some hope that my food waste or the commingled municipal solid waste can be pyrolyzed, because it is more or less giving me higher calorific value, even though it is not very high value, right? That means plastic has a very high calorific value, food waste has comparatively less, but if I mix food waste and plastic, of course we are getting sometimes something like a weighted mean to give a comparatively significant calorific value. But if you see the C by N ratio, C by N of this Indian municipal solid waste, it is very less. That means the mixed waste, even other waste, even without looking into the property, we know the mixed solid waste cannot be taken for a biological method. Obviously, we need to go for a segregation technique. Yes. So same way, if you see the ash content again in a commingled waste, the ash content is comparatively less, but we have more hope towards the higher volatile matter content. So I don't want to leave the pyrolysis technique because it can be applied only for the plastic waste or tire, but we will just think of some modification in the pyrolysis process so that we can accommodate all these municipal solid waste components. So again, going back to what the pyrolysis process will do to our feedstock if it is a biomass feedstock. So no, it's not a plastic or it's not a waste tire. So what will be the fate of a biomass feedstock? Of course, initially there will be a moisture removal, that is dehydration. So maximum we can expect the moisture removal to 100 to 150 degrees Celsius or so. And then the further increase in temperature will remove the hemicellulose component, which is easily decomposable fraction in the biomass. Then it will decompose the cellulose, and higher temperature 400, 600 or 800 degrees Celsius will give you the higher decomposition of the comparatively resistant, heat resistant lignin component to give it subsequent end product. So again, the question is still valid. Do we need to go for pyrolysis? We can improve the pyrolysis technique using different process parameters, right? So this process parameter starts from the feedstock itself. So we can alter or engineer the feedstock in different ways. Maybe we do by doing some pre-treatment to reduce the moisture, or the shredding or pulverization to reduce the particle size, or mixing different solid waste so that the composition can be changed or engineered. Now, after playing with the feedstock, Of course, the pyrolysis reactor, different operating parameters will also play the amount and quality of the end product. Yes, in that, one is the feeding rate, how much is the capacity of your reactor. That again depends on the heat exchange capacity, the heating system, and so on. Then reaction time, how long you are keeping your feedstock in the pyrolysis reactor. What is the inert gas flow rate to make sure that the reaction is taking place in the inert atmosphere. And what is the heating rate? This depends on the mode of heating. And what is the final temperature? Are you aiming at 300, 400, 600, 800, and so on and so forth? And the 3T principle is applicable here as well. That is temperature, time, and turbulence. Each of these more, the better will be the pyrolysis end product. Of course, by tuning these process parameters, we can alter the relative quantity of the biochar and the rest of the two products. That is the vapor which will be condensed to get the bio oil or the pie gas. Of course, all these operating parameters are tunable to give a different byproduct composition as well as the quantity. But how far your system is adjusted, it can be adjusted. How easy is the tunability of your system? And is the conventional pyrolysis addresses all these tunability challenges that we have to look into. And most obviously, the heating rate and temperature should be easily tunable, and we should be able to stop it at the required temperature. But most of the time when you go for conventional pyrolysis, the method of heating is conduction heating. So it is not like an on-off process. Very difficult to control the heating rate and temperature. Now, again, coming to the byproducts, as I have told earlier, the biochar, bio oil, and pie gas. Again, you may tell me, pyrolysis, we have to go for a lot of heat energy input, and it may cause some pyrolysis gas, which may be toxic, and we cannot release it to the environment and so on. But the studies have showed the biochar that we could produce in our lab also, the toxicity study showed there was very less heavy metal leachability. That is again because of the peculiar heating method that we have used. And then the bio oil component has high heating value. And again, depending upon the mode of operating parameters, you can change even the quality of bio oil. And of course, the pie gas major component is hydrogen. And if I can say this net process of pyrolysis adds up to the carbon capture. Because if you can see the normal carbon cycle, suppose I have the plant particle or the plant or the green grass that is coming out as biomass, and we know biomass or crop burning is one of the major source of air pollution. I should add it to the Delhi air pollution as well, right? The Delhi air pollution major component is the crop burning in the northern states like Punjab, like post clearance of the crop residues by mass burning. That is one of the reasons for Delhi air pollution, right? Because of the excessive carbon black or carbon dioxide that is the particulate matter that is being generated due to the biomass burning. So what it happens, all the carbon dioxide that is fixed by your plant is released back to the atmosphere by the biomass burning or decomposition. So it's just a cycle. So we are again getting the same CO2 that is released back to the atmosphere, adding up to the global warming. But if we go for pyrolysis, we are doing the carbonization process, and most of the components that can be converted to biochar, which is essentially a carbon, fixed carbon. So I should say if I am getting 50% of biochar in the pyrolysis, this 50% is just as a, we get it as a fixed carbon, which can be just dumped into the soil, or it can be used for different purpose, which we'll see later on. And only the rest, that is the bio oil or pie gas component, of course, we may be using it for burning in the later stage for energy production. And this will create a CO2 emission, but even then, the release of CO2 is only 50% compared to the direct burning of biomass. Now, when you do a conventional pyrolysis process, we can broadly classify this process into two, that is primary and secondary pyrolysis. So in primary pyrolysis, it is the initial breakdown of comparatively simpler molecules, and mainly this is the removal of moisture content, etc. So it involves the dehydration process, dehydrogenation, decarboxylation, etc. So the lighter component in your solid waste will be volatilized. But if you go for secondary pyrolysis, so it is not two separate pyrolysis, but two separate stages that happens in your pyrolysis process. So in the secondary pyrolysis, the product from the primary pyrolysis will again undergo secondary reaction, secondary decomposition, and this secondary pyrolysis can be easily tuned based on the catalyst or the atmosphere that you are providing for your pyrolysis process. And this catalyst can be the same, a homogeneous or heterogeneous catalytic reaction based on whether you have a solid or the gaseous liquid catalyst or so on and so forth. Right? Now, in this secondary catalyst, it is the complete cracking or thermal cracking of your heavy compound, which can form the smaller compounds like carbon dioxide, carbon monoxide, etc. And again, this can be tuned to get which byproducts you need. So if you don't need a complete volatilization, again, you can think of using a suitable catalyst for this secondary pyrolysis reaction to improve that particular quantity of that particular component. But can these processes, the primary and secondary pyrolysis stages, can be that tunable if you go for a conventional pyrolysis? There are many disadvantages when you go for conventional pyrolysis, which mainly use the electric heating system. For example, it has high energy loss, slow heating rate. Of course, it needs a long process time. And when you heat up your feedstock, parallelly the chamber is also getting heated up. Right? And there is a poor control of the heating process because we are just heating that heating coil, then it is the conduction heating to the feedstock, which may cause uneven distribution. So if it can tune or modify the heating rate and heating mode, that is the recent trend in advanced pyrolysis. So we are going in search of a high heating rate mode and good heating mode, which can come across, or we can avoid all these disadvantages of conventional heating. And one such advanced pyrolysis technique that we will cover in today's lecture, and there are many more as well. And one such method is microwave assisted pyrolysis. So as the name suggests, microwave is helping for pyrolysis. So microwave is used as heating source instead of the electric heating. So this is the typical flow diagram of the microwave pyrolysis unit what we have. So it has a limited minimal pretreatment that we are doing for the feedstock. That is come in water content. It is not at all necessary, but if you need, you can think of reducing the water content. We are not doing it because I'll come to that why moisture content reduction is not that important in microwave pyrolysis later. But we are just doing the particle size reduction. But even though we have given a drying unit prior to this, mostly we are not going for the drying of solid waste. Then it is grinded and fed to the pyrolysis reactor. So here we have the nitrogen flow meter, so which will ensure that inert atmosphere in the chamber. Then all fully controllable time, temperature, power mechanism is provided. And even the temperature can be measured using a non-contact sensor. So that will give us what temperature your feedstock is at a particular time. And once that time, the design time is over, we'll get the pyrolysis byproduct. The solid content will be separated through cyclone that we are getting the biochar. And then the gaseous vapors are condensed. So we are using water coolers. water cooler condenser to condense the pyrolysis oil, and then we have the pyrolysis gas. So this we have the collection oil pyrolysis gas collection system. Of course, this can be upgraded at different stages. Even bio oil or biogas can be upgraded at different stages to tune the quality of your end product. And of course, we are doing that biochar modification for its end use application as well. So there are different advantages, I should say, that is the transfer of energy in conventional pyrolysis is through conduction mode, but here it is conversion of energy. So it is a molecular level heating. In a microwave pyrolysis, unlike the conduction heating, so it is an in-core heating, or I should say individual molecule is heated up, and so we are getting a uniform heating, unlike the conduction, convection, radiation heating that is there in the superficial conduction heating process. And in microwave pyrolysis, at times we can hit hot spots. So this hot spot is a peculiar mechanism of electron that is jumping in the microwave pyrolysis field or microwave field that may give you an instantaneous temperature of around 1000 degrees Celsius or so for a fraction of a second. But that will also add up to the heating rate or pyrolytic treatment or pyrolytic reaction of your feed stove. And of course, it is rapid. I think I don't need to tell more about the microwave heating and conventional heating because we are practicing it at home, also in cooking in microwave oven as well as in the domestic conventional heating mode. And this process as well selective, because we know when we keep some food in the microwave oven and heat it up, that container is not heated up, but the food will be boiling or it's just burning it. So that way it is selective heating, which depends on the property of material. So in short, we can say microwave can cause rapid and selective heating at molecular level, unlike your conventional heating. So why is it so? Because we have the microwave. If you see the position of microwave in the electromagnetic spectrum, it is in the low energy region. But this low energy microwave can cause the polarization of the dipole molecule. So if you have dipole molecule in your feed stove, it will cause that polarization, the vibration of molecules, or if you have the free electrons, it will cause conduction of free electron and subsequent resistance. So that way, or a combination of these two, that is called interfacial polarization. So these three are the mechanism of microwave heating. So we can very well say a water which is a polar compound will be heated up compared to the dioxin which is non-polar. So same, if you have distilled water with more ions, with less iron, will not heated up compared to the tap water which has free ions, which can get heated up by the conduction process, right? So with this mechanism, if you just compare the conventional to microwave heating, we will get the in-core heating in the microwave. That is, individual molecule is heated up. So the core heating happens, unlike the conventional heating, wherein the heat flow is from outside to inside. Now, some of these feed stove may not be a good absorber of microwave. So in that case, you can enhance the microwave heating of your feed stove by using suitable microwave absorbers. So these are again some of the advantages of heating technology, which I have just covered in the previous slide, like faster reduction in the waste volume because of the rapid heating, selective heating, and it can also cause enhanced chemical reactivity due to some hotspot formation and so on. And mostly it can cause a decentralized treatment system because the footprint of your microwave treatment, pyrolysis treatment unit will be much less compared to the conventional pyrolysis unit. And it is flexible. As I told, the microwave heating can be easily tuned compared to the conventional technique, conventional heating technique. And of course, ease of control and energy saving. Again, you may ask me, we are having a lot of microwave energy to be given. But if you see in case of net energy gain in terms of byproduct, of course, we are slightly on the positive side in terms of energy gain. Now, As I told earlier, all the feedstocks are not microwavable. So for all feedstock, it will not get heated up. So all your waste will not get heated up by the microwave radiation. For example, there are conductors in your waste component. So the microwave will reflect get reflected from the surface of these conductors. That means it will not get heated up. So there are insulators, for example, like glass and ceramics. They will just allow the microwave to pass through it, or it will not get heated up. But there are some absorbers, so which can absorb this microwave. So this we call it as a dielectric or Low's tangent. It is termed in terms of Low's tangent. That is the amount of energy that is being captured by the material to that of the energy that incident on that material. That is Low's tangent. So if you have a very high Low's tangent for a particular material, that means it can get easily heated up. So no need to be worried about your waste. That is, if it is a conductor, if it is an insulator, if it cannot be heated up by microwave, of course, we can think of using some microwave absorbers. And most common microwave absorbers used are like charcoal, carbon black, activated carbon. Any carbon for that matter is a good microwave absorber. And let me see here the ice, water is also a microwave absorber. Now we can just think of, okay, we have very high component of moisture content, very high fraction of moisture content in your waste. So no need to worry. My microwave will help in making this water as a boon, because the water is dipolar, polar material. So it will get heated up. In turn, it will help me to heat up the feedstock in presence of microwave heating. Well and good. But the conventional pyrolysis that was applied for plastics, but coming to microwave pyrolysis, plastic is a very low microwave absorber. So we cannot directly convert our conventional pyrolysis technology to plastic microwave pyrolysis technology for plastic, because it is a low microwave absorber. But again, we can think of using some microwave absorbers like carbon black, activated carbon, even silicon carbide. All those things will add up to, can be mixed with your plastic to enhance the microwave process. And of course, like the conventional process, the temperature is from 200 to 1000 degrees Celsius or so. Inert atmosphere is required for the process, and uniform mixing is well and good for the distribution of the absorber and medium. Size reduction again will give you the uniform heat. So just to tell some of the microwave absorbers that we have used. So we are trying with different microwave absorber to heat up the food waste, rice husk, rice straw, and it's giving a prominent result. For example, if you have any carbonaceous material for that matter, is a good microwave absorber. Fly ash or water ash, the waste. Again, silica fume is another waste. Even the cement that is post-construction waste, cement was also giving us a good capacity for heating up for microwave. So you can think of even some of the waste as a microwave absorber to enhance your MAP process, microwave assisted pyrolysis process. So that means, say, let me take, I have one microwave absorber that is added to my feedstock. Suppose my feedstock is a non-microwave absorbing material, and here I have one microwave absorber. So that means now this absorber will absorb microwave, and later on it will be conduction heating, right? So this will be conduction heating. Now this conduction, with the conduction heating, now the temperature of this surrounding is improved. It will further conduct the heat to the outer surface, so on and so forth. Now this heating rate can be further improved if you are adding a little more of the microwave absorber. That means you can again tune the ratio of microwave absorber to your feedstock to enhance the heating rate. Right? So here you can see the increase in temperature, the heating rate, time, all these can be tuned based on the ratio of the absorber used. Now, how to do the process optimization? This is more or less same as that of the conventional pyrolysis process. Once the feedstock is fixed, once the feedstock to susceptor or microwave absorber ratio is fixed, again you can play with your process optimization, that is the optimizing the operating parameters. Of course, what should be the temperature, at what heating rate, what reaction time, or what should be the feeding rate, inert gas purging, so on and so forth, to tune your pyrolysis end product. And again, you can think of, okay, if I need to produce more biochar, what will be the optimum of this operating parameter? Or if my aim is to get maximum bio oil, how should I tune my operating parameters? And again, you can think of improving the byproduct quality in line with the pyrolysis process, or even you can think of post-treatment method to improve the quality of biochar, bio oil, or bypass. So now let me just give you some of the results that we have from our studies on biochar MAP pyrolysis, microwave assisted pyrolysis, which is done for different feedstocks. So here on left, you can see the food waste and plastic. So initially people were reluctant to see, okay, food waste can't be pyrolyzed. Of course, sometimes we have to even think of our role, that is biodegradable waste cannot be pyrolyzed. But then if you recall, yes, how we are collecting our waste from our individual household. Now we have that garbage bag into which we are collecting all the wet waste. And the next day morning, we will dump it into the waste collection bin. That will be collected and then taken to that management facility. So if you see the food waste management, of course, the food waste is collected. Most of the time, the food waste is collected in a plastic bag, garbage bag. That segregation is vital. So why can't we think of combining these two and taking it to a pyrolysis unit? Of course, conventional pyrolysis unit may fail, but we have this microwave, which has a peculiar technique to handle this excess moisture in the food waste. So we just thought in that way, and we did that food waste and plastic pyrolysis, and it was giving an excellent result. So here, if you see, with increase the LDPE content is improving the bio oil quality. Again, you can recall our previous slides, like plastic has high hydrogen content and less oxygen content, right? So high hydrogen content and less oxygen content will improve the calorific value of your bio oil. So that way, even if you have food waste with low hydrogen content and high oxygen content, by mixing it with plastic, slightly we are tuning the feedstock property, and the pyrolysis of this is giving you a good quality end product, that is bio oil. Now we have also done the pyrolysis of rice husk. So in this study, we have optimized the bio oil production, and of course, around 50% of bio oil could be generated with comparatively high quality. And in the rice husk, again, the biochar could be produced with an excellent quality compared to the carbonation or the conventional pyrolysis or torrefaction process. Yes, as I have told earlier, we can tune the byproduct. We can tune the relative ratio of the quantity of byproduct very easily in a microwave system, because we have a good control over the temperature, heating rate, etc. So here, just to give an example, so let me just explain with this particular one. Here we have the bio oil, that is the blue color line is signifying the bio oil. And here we have the non-condensable gas as well as the biochar. So as you see, the residence time, that is the time for which our sample is kept at a predetermined temperature. That means at 550 degrees Celsius, we are keeping the sample. Again, you can see the time for which the sample is kept. It's only few seconds compared to the minutes or hours in the conventional heating, right? So at 550 degrees Celsius, even if you have 13% of plastic in your food waste, so this is the yield with respect to residence time. So of course, there is like a relative yield of each of this. So we can think of optimizing or keeping a particular value of each of these parameters based on the type of end product you are targeting at. And same is the case with temperature. The lower the temperature, you can get more biochar. But if you increase the temperature, say 500 to 600 degrees Celsius, the bio oil component will be more. If you further increase, most of them will get volatilized again by secondary cracking, and you can get the biogas as the major end product. Again, it is up to you to tune which byproducts you are aiming at. Now, are we getting a good quality bio oil? Of course, we have to give some compromise to the quality of bio oil, because this depends on, obviously it depends on the feedstock property. But since we are mixing the food waste, because food waste, as we know, it is not a good pyrolysable material. Only because of the peculiar property of microwave, we have pyrolyzed it, that too again in presence of plastic. So this mixing could improve the property to some extent. So here I can see, so here the one important thing is we have optimized the total acid number. Total acid number should be very less than number. So here you can see it is around, sorry, it is 17 or so. So more the acid number, the higher will be the corrosivity. But most of the organic waste is not meeting the TAN standard. But when you go for food waste combined with plastic pyrolysis, the two in a microwavable system, we could give a better quality bio oil compared to the conventional biomass pyrolysis. But even then, it is not meeting the ASTM standard of using it as a biofuel or gasoline. But of course, this can be used as a burner of fuel for heat exchanger or so. But we haven't stopped here. Of course, this quality is further improved by catalytic dehydrogenation. Our partner from Belgium, University of Ghent, Belgium, they are helping us in upgrading this part, and which could give us a bio oil which is in par with the quality of gasoline. But only from microwave pyrolysis, we could improve the quality more or less close to the gasoline, and we are doing the dehydrogenation, catalytic dehydrogenation to meet the in par standard with the gasoline. Now, if you go for biochar, what should be the property that you are aiming at? So suppose you want to pyrolyze your solid waste and you are not interested in bio oil. Okay, we can tune it to get a maximum amount of biochar. But in biochar, again, it depends on different end products, end use of biochar. Right? We can characterize the biochar for its morphological characteristics. We can use SEM, scanning electron microscopy, for the microscopic analysis. You can even do EDS, will give you that elemental composition. Surface area, for example, if you want to use biochar as an adsorbent, it is a better adsorbent for many of the pollutants. So you can go for surface area analysis like BET analyzer also. And toxicity analysis is vital, because if you are just disposing this biochar into a soil, it should not leach toxic substance to the land. Or if you are using it as an adsorbent for water treatment or wastewater treatment, the biochar should not add any toxic material to your water sample. So that way toxicity should be tested. And you can also use this biochar as a heating fuel. So in that case, the HHV and fuel ratio. Fuel ratio is the ratio of fixed carbon to volatile carbon can also be assessed. So if you see the rice husk that we have pyrolyzed using my MAP process, here you can see the property of rice husk. The rice. Am I audible?
Yeah, yes, Remya, you're audible.
Okay.
You're audible.
Yeah. Okay. Yeah. So here you can see the property of rice husk. Prior to pyrolysis, it has a very low heating value. Fuel ratio, that is fixed carbon content to volatile matter content, was much less. And the next property is O/C ratio. Oxygen to carbon ratio was high, around 1.5. Very small surface area. The rice husk as such has low surface area only, and the pH of near neutral, around 6.71. Now, when the microwave pyrolysis process was optimized. And in the optimized condition, we could get a pyrolysis product, that is biochar, which has highly carbonized fuel, the higher heating value, in par with the coal. Indian coal has almost the same heating value, 25 to 30 megajoule per kilogram. So it was a good biochar with high heating value, improved fuel ratio, oxygen to carbon ratio was significantly reduced. So lesser oxygen, of course, it is giving us a hint that it has high heating value. And you can see the surface area, tremendous improvement in the surface area, and we could use it for the adsorption of several compounds like even nitrate and phosphate removal from wastewater as well. And the improved pH was also observed. So it is giving a hint, of course, if I need to use it as a soil amendment in an acidic soil, it may give you some improvement or soil conditioning. And further, if you see the characteristics of this rice husk and the biochar, the moisture content, because in rice husk itself, the moisture content is very less, it's almost a dry product. Volatile matter content is converted to fixed carbon. So its volatile matter content is completely reduced, and you can see the corresponding increase in the fixed carbon from 18 to 52%. Tremendous improvement in the carbon, decrease in the oxygen, high improvement in the bed surface area and heating value. Right? And the other aspect we are looking at is the modification of biochar. So maybe you can use the biochar as such. Of course, it is giving a good removal of pollutants from wastewater. Like it can be even used as the adsorbent for nitrate. And this nitrate adsorbed biochar can be later used as a fertilizer, because biochar, if it is not leaching, it is a completely pure carbon with enhanced porosity and so on. If nitrate is absorbed on it, it can be used as a nitrogen fertilizer. Right? But to further improve the biochar property, we are again post-modifying the biochar, either just by steam activation or gas purging. So this is done just to improve the pores that is blocked by the amorphous carbon also during the pyrolysis process. And you can even think of other modification process like alkali modification or acid modification. In either of this, we can play with the surface functional group. So it may have more OH group or more carboxyl group based on whether you are going for alkali or acid modification. And this can be used for the removal of the other opponent ions from the wastewater. And further, we have even done the magnetic modification, that is making the biochar with some magnetic property. Right? So if you go for magnetically modified biochar, the advantage is that post-treatment separation can be done using the magnet. So just to enhance the magnetic separation of the biochar after the treatment process, even you can make it, modify this by the magnetic properties, improving the magnetic property using iron or some ligand. So what to do with the bio oil? I have just given a glance earlier. So it's a dark brown liquid. Again, based on the tunability pyrolysis, you may get different fractions of bio oil like wax separate and light fuel separates and so on. Or again, based on the operating parameters, you may get a completely dark brown liquid and so on. Again, tunable based on your end use. And then it can be used for boilers or surface furnaces for direct burning, hot water generators, and with some improved property or even with some catalytic conversion, it can be even used as a blend directly as a gasoline or biofuel, or it can be blended with a conventional fuel. And biochar application, as I have just mentioned earlier, biochar has high pH. So of course, it will give you the soil conditioning opportunity. Acidic soil can be ended with, and it is also improving. Many biochar has shown to improve the water holding capacity of soil as well. Then the surface area. Of course, surface area of biochar itself is more. And if you are going for microwave pyrolysis, the peculiar microwave property is making the biochar more porous. So the surface area is tremendously improved with increase in microporosity as well. So it can be used as adsorbent. So environmental remediation for removal of, say, heavy metals or other organic pollutants. And of course, it is reducing the CO2 emission, right? So low GHG emission and high carbon sequestration if you convert your waste into biochar. And of course, it can be used for the physical properties because of its high porosity, high surface area, and even water holding capacity. This water holding capacity in turn can be used for the soil. In the agricultural crops, if you have good water holding capacity, it is well and good, right? Then better soil growth due to pH adjustment of the soil, and microbial abundance, because it is a carbon material with good porosity, so the soil microbes growth will also enhance, and it can be used as a slow nutrient release source. As I have told, we could get a good nitrate removal from wastewater using the biochar, and this biochar was the nitrate adsorbed biochar was later used for crop productivity, and it gave a better result. So tremendous opportunity for biochar as well. But then all these advantages are there. But what is the stage of a commercial microwave pyrolysis plant? Of course, there is no bigger commercial establishment in our country as of now, but you can see there is a mobile pyrolysis plant that is up and working in European Union. So it is, in turn, it is a mobile microwave pyrolysis plant, thanks to the small footprint that is required for the microwave heating system in a pyrolysis process. And of course, it can handle the different variety, except the glass or metals. Almost all can be fed into the microwave pyrolysis unit. Only thing is you have to use appropriate microwave absorber. So now we are working on it. We have done almost all the lab scale tests for different biomass, pyrolytic conditions, and byproduct distribution. And scaling up is done, of course, not for pyrolysis. That same torrefaction, we have done scaling up for around 100 kg of rice straw per day. It is almost going to be commissioned soon. So that scalability is done. And once the scalability, and I should say that scalability of microwave-based water treatment or solid waste treatment technique is much simple compared to the conventional method. So once it is scalable, of course, we can think of large industrial scale application, or even for a decentralized treatment system for MSW. So just in brief, of course, as we know, there is a need of efficient solid waste management method because we are running in short of land availability. And of course, we need to treat the huge amount of waste generated in a day-to-day basis within a shorter time. So pyrolysis is one good alternative because it has faster reduction of waste in terms of volume as well as in terms of the usable end product. So I can say this is a waste to clean energy technique because most of the end product that we get from the pyrolysis process is environmental friendly. Now to cater the higher food waste composition or green waste composition that is mixed with the plastic or tire waste, we can think of advanced pyrolysis like microwave pyrolysis. So in addition to catering different types of waste, it is also giving us better control over the process parameters as well as on the byproduct quality. And it has several environmental applications for the end products. So it can be used as a heating source because of calorific value. Even the biochar can be used as a heating source. Bio oil is, and pie gas can also be used for generating heat, and the different environmental application for soil remediation or water treatment, wastewater treatment, so on and so forth. So let me stop here. Thank you so much for listening to me.
Okay, thank you, Remya. So there are a few questions in the chat box. Shall I read it out one by one?
Yes, no.
So that you can.
Yeah.
So some of the questions are already answered. They were asked initially and they were answered through during your presentation. So those questions I'll skip.
Okay.
So one person is asking about the future application of biochar. I mean, he asked about the possible applications that already you have explained, and then any future applications he's asking of biochar.
Yes, I think I have to just focus more on this. So future application is not one or two. My slide is visible, right?
Yeah, yes.
So plenty of applications. So this is again restricted to the environmental applications because the biochar as such is a good carbonaceous material. So we can think of replacing this biochar to the conventional application that we use for, say, granular activated carbon, GAC, right? So as a good adsorbent. But I should say the biochar that has obtained from the microwave pyrolysis is a good adsorbent than the commercial granular activated carbon because of its high porosity and surface area. So that is one aspect. The other thing is its calorific value. The biochar properly tuned pyrolysis process of the agricultural biomass mostly. That is giving you a biochar which has a heating value in par with the Indian coal. So we are using this coal burning for thermal power plant, right? So we can use this biochar even for burning for that heat because of its calorific value. That is one aspect. Lot of application is there in that soil conditioning because say biochar has good water holding capacity. So that is good for the lesser irrigation requirement due to that water holding capacity. And then it is improving the soil microbes, again benefiting the crop production and so on. And if you say in a broader aspect, this biochar can also be used as a supporting material. Even we are trying it for as a supporting material for nanocatalysts. For example, if I want to do the photocatalytic treatment, maybe I'm using titanium dioxide in nanoscale, nano TiO2. It is very difficult to separate from your wastewater or water after the treatment. The separation of post-treatment separation of TiO2 is difficult. So in that case, we can have this biochar as a supporting material. We can adopt different methods to support this TiO2 on biochar. Then this will act as a support material for the TiO2 based photocatalysis or even ZNO based photocatalysis or so. So the biochar will help in absorption of pollutant. Then your TiO2 will cause degradation of pollutant. Further, this biochar based TiO2 can be easily separated from the aqueous phase after the treatment. So many other applications. I'm just listing few.
Okay. Then there is another question from Gautam B. As plastic and rubber are the polymers of organic compounds, how come the air pollution control is ensured in pyrolysis process?
Yes, I should say the air pollution control is required in conventional pyrolysis unit. So after pyrolysis, you have that cyclone separator first. So this cyclone separator is removing the solid part. Then you have the vapors. The vapors are either going through that catalytic conversion technique or you need some scrubbers. Scrubbers before it is being removed to atmosphere. So again, that air pollution control strategy is to be adopted if you are going for plastic pyrolysis. That is being adopted in all the existing commercial pyrolysis plants, and they are running with the compilation with the solid waste or plastic waste handling rules. So we need to have that scrubbers, but what we have experienced in microwave pyrolysis of food waste and plastic, majority of the fraction was hydrogen. Even the plastic is pyrolyzed along with food waste, and we have used different susceptors, that is microwave absorbers. Even this microwave absorbers will help in tuning the byproduct. So when you use silicon carbide or when you use fly ash as absorbent, the hydrogen content in the pygas was much high compared to other toxins. So of course, we have to go with this air pollution control measures if you are going for the pyrolysis.
Then there is another question. Yeah. Yeah. So there is another question that is from Sudhanshu Suraj Kamath. So he's asking, is pyrolysis even an alternative to be considered to manage food waste? It will be very expensive in any situation. Biomethanation is the only best option for that. That is what, there is a question and also his opinion. So
of course, I should say the more you go close to nature, it is well and good. Biodegradation should be the first and best preferred method for all solid waste management. Yes, we are going more close to nature, not much complications. So in that way, it is better. But just if you focus on the tremendous amount of solid waste that is generated and the way it is collected. So most of the time in solid waste management, the main bottleneck is the segregation. So this segregation is very vital for the biological method, which is more sensitive to the other operating parameters as well as the feedstock. But when you have a mixed solid waste, it may have some toxic or a biorefractory substances as well, which has to be completely segregated and given for that biological treatment methods. So if you can do it, it is the best option possible. But to handle the higher amount of waste, which is mixed with all this non-toxic, non-biodegradable waste, we are just thinking of some alternatives.
Okay. Then Remya, there are many requests asking you to share the PPT if possible. Anyway, that we will see. I will contact you if it is possible or not. That we'll take up later. Then can microwave assisted pyrolysis be applied for medical waste?
Medical waste, again, we have just done, but medical waste pyrolysis, microwave pyrolysis is also done, because now I think this will be a very relevant question. Medical waste, as of now, the COVID pandemic waste is mainly incinerated. So we are getting the heat energy recovered, but at the same time, the toxicity, the main thing is it can be pyrolyzed. Of course, it can be pyrolyzed because if there is a non-pyrolyzed, most of the time the PPE or the gloves, all these are plastic for its material. It's a polystyrene, polypropylene, polyethylene, all these are coming along with the medical waste, gloves, shield, and so on. That can be pyrolyzed, but the question is the biochar. Most of the time, the biochar obtained from this waste may have toxicity. So it will reduce, obviously, the quantity of waste. We may get all these component fractions, but the end use, the usability or toxicity should be tested.
Okay. Then Bhavi Patel is asking, can we use microwave energy for advanced oxidation process? And if yes, what microwave absorber we need to add into the system? Microwave for AOPs.
Yes, AOPs. Yes, we are also doing it microwave for AOPs. We could do it for photocatalysis. So if you have, say, biochar or even any carbon material is a microwave absorber. So if you have, say, TiO2 based photocatalysis, then support that TiO2 on a microwave absorbing material. For example, TiO2 on GAC, TiO2 on graphite. All this will absorb your microwave. Then you can just take your photocatalytic system into the microwave reactor. But if you are going for photocatalysis, again, we need to have a special microwave lamp. Conventional lamp will work, but it is better to have an electrodeless discharge lamp that is again commercially available. That means the EDL will work. It's an electrodeless lamp which will emit UV in presence of microwave. I think that answer will be beneficial for those who are working with photocatalysis. Maybe they know the principle, the UV generation is required for photocatalysis. So in microwave-based photocatalysis, you can use that EDL lamp, electrodeless discharge lamp, as a UV source. then use a carbon material like GAC, then you can do that photocatalytic process. And if you don't have any of this absorber, even simple microwave H2O2, hydrogen peroxide is giving a better results for the removal of pollutant. So that is microwave oxidation. Microwave H2O2 or even microwave with persulfate, all this is giving good result for oxidative removal of pollutant.
Yeah, then there is another question that is from Manoj Singh. Do worms eat biochar?
Do worms eat?
Eat biochar. So that is what he wanted to know.
So do worms eat means worms usually need volatile carbon, right? So based on the efficacy of your pyrolysis process, most of this volatile matter is converted to fixed carbon. So it is just giving a support media most of the time. But again, we have even based on the extent of carbonization, there may be some simple volatiles that is present on the surface of biochar that can be eaten by worms. But otherwise, it is not a harm. It will just act as a home for microbes, if not a source.
Okay. Then Remya, I have one doubt. Like, will this microwave assisted pyrolysis on waste containing high moisture content, will that affect the quality of the gaseous output from pyrolysis? Because anyway, that moisture content has to go somewhere. So will it have some impact on the gaseous?
Yes, definitely. Yes, definitely it has. So if you directly take the food waste with pyrolysis, food waste alone can also be pyrolyzed using a suitable microwave absorber. But then the thing is, the bio oil may contain around 70 to 90% moisture, I would say. Because even after secondary cracking also, your moisture is still remaining in the sample. Right? So that way it has that moisture content if the food waste alone is pyrolyzed. So what we are doing is it is mixed with plastic tremendously, that the net moisture content in the feed is reduced because plastic has say less than 1% moisture. So in that way, if you are mixing it with plastic, the net moisture content of food waste is reduced. Or if you do with the wood dust, sawdust, that is again reducing the moisture content. So that way, if you tune the feedstock without completely like preheating, that will solve the bio-oil quality improvement to some extent. The other opportunities after pyrolysis, the vapors can be taken through a suitable catalyst or demoisturization can be done so that you will get the bio-oil component separate.
Okay. Then what is the what do you say that the quality of that oil for use as a lubricant? Is it possible? The viscosity,
Yes.
for example?
Yes, viscosity, yes, it is a good lubricant, but I should say then we have to think of, I cannot blindly say all this can be used as a lubricant because it also depends on its total acid number, TAN, because some of these will have corrosive nature. So that way we have to tune that. So based on the end use, of course, we cannot directly use the bio oil for different end use. We may need to tune it using the suitable catalyst. So what we are aiming at here is maximizing the quality, the quantity, and that quantity, some role we are also playing in changing the quality in terms of using different microwave absorbers. For example, the quality of bio oil we get by using GAC as microwave absorber. That means food waste, plastic plus GAC. If you pyrolyze this, the quality of bio oil, you will get a quality of bio oil. But when the same food waste and plastic, if you pyrolyze with silicon carbide, then you are getting some different quality bio oil. So that way we can give some tunability to the bio oil quality by changing the microwave absorber or microwave susceptor. But of course, you may need to go for an upgradation process to tune to meet the different quality of your end use.
Okay. So modification to which side will be easier? Like because on one side you are comparing with gasoline to be used as a fuel, and now I was asking about using it as a lubricant. So modification on which side will be easier, like as a lubricant or as a fuel?
It is as a fuel. As a fuel,
Okay.
it is more easy because it is very difficult to tune that tan value.
Okay.
So that way we can more tune it towards improving the heating value.
Okay. So now you were saying that the heavy metal concentrations were less in your biochar, right?
Yes.
Okay.
The leachability was very less. So because it was mostly biochar, food waste and plastic.
Food waste
So
and
again,
plastic waste. Okay. So leachability was less, but otherwise, did you see that in your ultimate analysis also? The heavy metals were there, maybe even though it was not leachable, was it there in the matrix?
yes, it was slightly there, but it was in the matrix. So we have done several leachability study, toxicity analysis as well. So using toxicity analyzer, so that way the leachability was less, significant.
Very less. Okay. So any studies on its use as a soil conditioner? We were talking about the moisture holding capacity of the biochar, etc.
Yes,
So do you conduct any studies there, or?
Yeah, we are doing it now. We are using this not only for soil conditioner, even for briquetting. Biobriquetting is done, and soil conditioner as well. So we are just seeing that crop productivity improvement, water quality improvement, and the soil pH. So all the soil conditioning, how it is getting affected.
Okay. Any more questions from the participants? You can directly ask. All the questions in the chat box are over. So if some of the participants would like to, or if they would like to add something, we have some time left. So you can add, or you can ask questions, or you can make your points.
Yeah, definitely.
You can unmute yourself and then take part. Then there are many messages appreciating your presentation. So I didn't read out that, but probably you might have seen that. A number of messages congratulating you for the excellent presentation.
Thank you so much.
Good afternoon, madam. I have a question here.
Yes.
It is
Here,
not.
who is talking?
Introduce yourself and then you're audible, but please introduce yourself first and then
please introduce.
I am Gautam here from National Engineering College, Kovilpatti. I am working on advanced oxidation process. As you said, the speaker was related to the advanced oxidation process also. I have a doubt related to that. As I was working on the Fenton and photofenton process, the main problem with that is the pH control. It is mostly working on the acidic pH like a pH 3 or 3.5. Does there any solution for that to work in a normal environment?
Working in normal environment.
Yes, without reducing the pH or increasing the pH.
So mostly the Fenton process, so I may not be the expert to comment on this, but the Fenton process is more efficient in the acidic pH. As you said, it is 2 to 3 will be the most efficient pH. But then we have to compromise on the maximum efficiency if you are going for a higher pH, somewhere in the higher side.
Okay, ma'am. Thank you.
And Gautam, we have actually one presentation from Nitish, who is actually an expert in Fenton process. So maybe you can
sir.
ask him also. Remya is also an expert, but then we have a person who has been working in this area for many years.
Is,
Nitish, yeah. So he's
purely working on electrofenton, photofenton. Yes.
Yes.
Okay.
Good afternoon, ma'am.
Yes.
Good afternoon, ma'am. I'm Rashmi from Bangalore, BNMIT. Very beautifully presented, ma'am. Thank you.
Thank you. Thank you.
So any more questions, any more comments? So I think if there is no more comments, Ananta, can you take over? And so anyway, on behalf of the organizers, on behalf of the Department of Civil Engineering, meanwhile, to the participants, Remya was our colleague for a few years, and then she shifted to IIT Bhubaneshwar. So we know her personally. So she readily agreed to our request for making this presentation. So thank you, Remya, on behalf of the Department of Civil Engineering and on behalf of the organizing committee and on behalf of the participants also. So thank you for this excellent presentation. We do look forward to continued cooperation in our future programs also. So thank you. Our next session is, I think, Ananta, please take. Ananta, are you here?
Yes,
Sir, I
thank
think
you so
Ananta
much.
has not gone back, sir.
Okay.
So can I leave?
Yeah. Thank you,
Oh,
Remya. Thank you, Remya. Ashwati, would you
yes,
like to
thank
add
you.
something?
Thank you, ma'am. It was really like a very well explained talk. Thank you very much.
Thank you for once again giving me opportunity to be in NIT Calicut, at least virtually. Thank you so much.
Okay.
Thank you.
So thank you, Remya. So now to the participants, our next session will be at 2:30 as usual. So we will join back a few minutes before time. Okay, so we will definitely send a message in that group. All the same, you can join in time. Anything more? So we will close the session. Is the poll over?
No,
No,
sir.
sir.
It's still running. It's still
Okay,
running.
Sir, recording to be stopped.
Yeah, yes.
Parts